Hi guys, so this is the question number 3 of an NMTC 2 Inter. So let's see this question. In this we have given AB is equal to AC, right, and I is the incenter of the triangle. Then we have given that the circle 1 has the center A and radius AB. So we draw a circle with the center A and radius AB, and AB is equal to AC, so that circle passes through C also, and let's name it as a circle 1. Then we have a circle 2 which we draw using I as a center and IB as a radius. So again IB is equal to IC, so that circle passes through C also. So this green circle is our circle 2. Then we have a third circle which we pass from I and B. So we can draw infinite many circles passing through 2 points, and so means this orange circle is a variable circle, and we have to draw it in a way that intersect it intersect the sides, the remaining two circles, green and that the bigger circle, circle 1, at P and Q. So we just draw any random circle which passes through I and B, which intersect them P at P and Q. So bigger circle or circle 1 at P, circle 1 at P, and the circle 2 at Q. And if we extend IP and BQ, they intersect at R, and we have to prove CR is perpendicular to BR. Okay, so this is our diagram in which we have to prove CR is perpendicular to BR. Now as R is the intersection of IP and BQ extension, and you can see we can apply the power of a point on this. RQ into RB is equal to RP into RI. Now if you observe RQ and RQ into RB is also a power with respect to green circle, because Q and B are on a green circle also. So I can write RQ into RB, and the center of green circle is I, right? The center of a green circle is I. So I can say it is Ri square minus radius of this green circle, because we know power of a point is like if we have a point P, then its power with respect to any circle is PC square minus R square. So C is the center of the circle, so PC square minus R square. So in this case, for a green circle, center is I, so Ri square minus its radius. Can I write radius is as a IB? So this is what we have. So Ri square minus IB square is RP into Ri. So now if we rearrange the term, if I pick RP into Ri term to the left side and IB square to right side, so we get this. So now if we take Ri common, it is Ri minus Rp is equal to IB square. So what is Ri? Okay, Ri we can write as a IP. We can write Ri is that is IP plus PR. So this will convert it to Ri into IP is equal to IB square. Okay, so we have Ri into IP is IB square, or I can say IR into IP is equal to IB square. So now from this relation, can I make a triangle circle? Sorry, can we draw a circle which passes through that BPR? If we draw a circle passing through BPR, then from this IR into IP is equal to IB square. Can I say IB is the tangent of that circle? For the circle which passes through BPR, from IB square is IP into IR, that IB is a tangent of this circle, right? So for this circle, if it is a tangent, if it is tangent, then using that alternate segment theorem property, can I say that the as this BP is the chord of that green circle, this angle is equal to the angle made by the chord BP on the circumference of this green circle. So these two angles must be equal. Angle 1 is equal to angle 2 by alternate segment theorem, because IB is a tangent, so IB makes an angle 1 with BP, so BP makes an angle R, BP makes a same angle at R. So angle 1 is equal to angle 2 by alternate segment theorem. Now again, using that same condition, as we have IP into IR is IB square, and as IB is equal to IC also, so this is equal to IC square also. So in now we can draw a circle. We can draw a circle passing through PCR, and IC is a tangent of that circle, right? Now in this, if you see CP is a chord of this circle, then this angle should be equal to this angle. So angle 3, if I say this angle is 3 and this is 4, so angle 3 is equal to angle 4 by alternate segment theorem. So if you see in the previous slide, we see this is the angle 2, and now we have said that this angle is 4. So this angle is 4. So angle 2 plus angle 4 is basically equal to angle 1 plus angle 3. Angle 3 is this one. You can draw it here also. It is angle 3. Right? So if we somehow prove that angle 1 plus angle 3 is 90, then we are done. Right? As our angle R is equal to angle 1 plus angle 3. So if we somehow prove that angle 1 plus angle 3 is 90, then we are done. So angle 1 made from these two parts, and angle 3 made from these two angles, right? Now we know this is B by 2, this part of angle is C by 2. We have to just figure out these two parts of the angle, this angle and this. So we have already B by 2 plus C by 2, we have to find this X plus Y. Now if we see these B, P, C points, they lie on which circle, guys? This lies on a bigger circle, circle 1, BPC. So if I see that angle X is made by the arc PC, angle X is made by the arc PC, and Y is made by the arc BP. So X plus Y, X angle plus Y angle is made by BP plus PC, or can we say it is BC arc. Total angle is made by the arc BC. So the arc BC makes an angle A at the center. The arc BC makes an angle A at the center. So on a circumference, it makes an angle A by 2. So X plus Y is A by 2. Now if we see the total sum of these angles, B by 2 plus X plus C by 2 plus Y, it is B by 2, C by 2, X plus Y is A by 2, which is 90. Right? So this is how we can prove this.